Victor.
Yes. So I was amazed by the talk by Professor Cohen, and that inspires me to keep on working on Taylor's law. Now, given that he has done such a great job at motivating Taylor's law, I am going to go a little fast over the motivation. I have some different motivation, but some of it is the same. And I will talk about the mathematics or the proof of the result that is used to prove Taylor's law for infinite means. So I give a detailed proof. The proof is based on a trick by Karamata in the 40s. Okay, so let me start. So Taylor's power law is actually an extension of the coefficient of variation. So let me talk about the coefficient of variation first. I am actually going to talk about the squared coefficient of variation. The squared coefficient of variation is defined as the sample variance over the square of the sample mean. The squared coefficient of variation provides a measure of dispersion which is invariant under scale change. Remember what actually Taylor's law is also invariant under, if we multiply the variables by a constant, the shape of Taylor's law remains the same. The constant changes, but you still end up with the same alpha value. So you have the variance over the sample mean to the alpha. If you multiply the variables by a constant, you end up with a constant times the variance over the sample mean to the alpha. In that sense, can you update up the turn pages? Now I want to see what that means. The pages are not turning. Is that okay?
Yes.
Okay. Okay. So now Taylor's power law, as I said, is an extension of the coefficient of variation. It is an important criterion used to describe the dynamic of populations. It was first observed as an empirical pattern in ecology, where it was noticed that the variance of each sample was approximately proportional to a power of its sample mean. An important property of Taylor's law is that it is invariant under scale change, as I described before. So if you multiply the variables by a constant, the sample variance over the sample mean to a power will remain the same up to a constant factor. Now, Taylor's law has been widely shown to be the source of many or explain numerous phenomena, including growth in which samples of multiple locations at points in time replicating over several points in time. Now, this is important, for example, in census studies. Okay, so Taylor's law has been used as a tool in studies in demography, biology, physics, and several others. Now, several papers have been, more than 2,000 have been dedicated to the study of Taylor's law. Important surveys on the topic are by Kendall, 2004, Eisler, 2008, and Meng, 2015. This talk is partly based on joint work with Mark Brown and Joe Cohen, as Joe mentioned before. Okay, so what is the setup? Suppose that you have Xij to be a double array of non-negative random variables. uh, probability xij equal to 0 is equal to 0. We let the sample mean and the sample variance be denoted by, so we take the sample mean at j to be the sum of xij to I going from 1 up to nj over nj, and Sn square of j equal to the sum of xij bar square I going from 1 up to nj over nj minus 1. So now Taylor's law is said to hold with exponent alpha if the log of Sn comma j square is approximately a constant plus alpha times the log of xn j bar for nj bigger than or equal than 2 and j equal to 1 up to m for a finite fixed constant. Okay, so the innovation in our work, typically in studies of Taylor's law, people plot the log of the variance against the log of the mean of the sample average. We actually study the properties of the variable Sn comma j square sample variance at j over the sample mean to the alpha at j. So we call this a self-normalized variable, and there are advantages to working with this. This looks more like the coefficient of variation, and the variances that are obtained are smaller than losing logs. Okay, so our main results are explicit formulas for the expected value of Snj square over x bar nj to the alpha and the variance of Snj square over the sample average to the alpha for j going from 1 up to n, involving integrals of the Laplace transforms of the distributions of the original variables. So the Laplace transform always exists. Whenever it exists, we have an explicit expression in terms for any random variable that in our case, we are working with IID, but we have extended this with Paul Ducan and Yahya to the case of weakly dependent variables. So as an application, as I said before, we obtain a measure of dispersion of the double array around the sample means. An illustrated example is given for the exponential distribution for which a simulation study shows that some small sample sizes, so when you have a small sample size, the variance of the log, remember the typical approach to Taylor's law involves logs, is going to be bigger than the variance of Snj over xn bar to the alpha. Okay, so we believe that this approach to Taylor's law complements what is being used in applications, and it can be useful. Okay, so we treat Taylor's law as an inverse problem. That is, we say that Taylor's law holds with parameter alpha for all distributions fj for which the expected value of Snj square over xnj to the alpha, xnj bar to the alpha is equal to a constant f of the distribution of x, alpha, n, and j for all j. So this is a constant that runs over, that is fixed for all j. Okay, so this basically in the context of what Joe Cohen spoke, this is valid as an approximation, but when you take the expectation, you get an exact formula. So I am going to show an example of how to calculate the expected value of Snj over x bar to the alpha for the exponential distribution and show that Taylor's law holds for this distribution when alpha is equal to 2. So rather than working with several samples, I am going to focus on the expected value of Sn square over x bar to the n to the alpha. Now, I want to remark something that is not on the slide, and that is that because of linearity of expectation, the expected value of this quantity is the same as the expected value of Sn square over x bar n to the alpha over many replicas of that random variable, and the replicas can be dependent, arbitrarily dependent. So what we have allows us to make a statement about Taylor's law in the case where the sample mean, the sample variance over the sample mean to the alpha are dependent across samples. Okay, this is done in terms of the Laplace transform of the random variables. When this expectation is equal to a constant for parameter alpha, for all distributions for which this is approximately a positive finite constant, we say that Taylor's law holds. Now, going back to the coefficient of variation, we recall that if we have the mean not zero and the variance finite, then it is common to call the variance over the mean square to be called the square coefficient of variation. Since the variance of the random variable x bar 1 over nu, it is unitless. The natural estimator of this quantity is the one that we use, which is Sn square over x bar square. It is easy to see that when the x's are non-negative, the expectation is given by kf2n, where f is the distribution of the variables. Therefore, connecting our results to the coefficient of variation. Okay, in this case, coefficient of variation is defined even for negative variables, but our technique requires non-negativity, and as Jo Cohen mentioned, it allows us to, because of cancellations, it allows us to treat cases in which the variables have infinite means and variance. So I am going to be a little bit more formal. This is the main result. So our main result is as follows. We take a sequence of IID non-negative random variables, and we let alpha bigger than 0 to be a constant. So we actually show a closed expression for the expected value of the sample variance over sample mean to the alpha. Okay. So as a function of Ln, everything else an alpha. The distribution is not involved. Okay, so this expectation is not always finite. There are some conditions that need to be met, very weak conditions, involving the expected value of the ratio of x bar n to the alpha. But the Laplace transform always exists. Okay, so the Laplace transform is defined as the expected value of e to the minus lambda x, and we denote it as phi of lambda for all lambda bigger than 0. Okay, so this is the main result. So the expected value of Sn squared over Xn bar to the alpha is equal to this double integral. So we take n to the alpha over gamma of alpha, integral from 0 to 1 of this function of lambda, which is lambda to the alpha minus 1, phi of lambda to the n minus 2, the second derivative of the Laplace transform at lambda times the Laplace transform at lambda minus its derivative squared. So it's the integral over d lambda. Now, I want to remark that what we have done goes beyond Taylor's law. It is not, Taylor's law holds when this expectation is fixed for a power of alpha, so one has to find the power of alpha that applies, but this result holds for all alpha bigger than 0 when the expectation is finite. So as I mentioned, the main trick to proving this result is something that Karamata noticed in the 40s, which is that a property of the gamma density, which allows you to take the x bar to the alpha from the bottom of the problem to the top, as I will describe next. So the gamma density has the property that 1 is equal to beta to the alpha. So we have a gamma density with scale parameter alpha and shape parameter beta. So in this case, we have that 1 is equal to beta to the alpha over gamma of alpha. The integral from lambda equal to 0 up to infinity of lambda to the alpha minus 1 e to the minus lambda beta d lambda. Now, here I write the mean of the gamma distribution is alpha over beta. The variance is alpha over beta squared. The coefficient of variation is equal to 1 over alpha. And special cases of this is the chi-square and the exponential, so the results apply to those variables also. Now, here is the proof. The first lemma is based on Karamata's result. If you think, so what we have is, if you think as the variables as constants, and you take the sum of x sub I to the alpha to be a constant, then the property of the gamma distribution tells you that this is equal to the integral of 1 over gamma of alpha times the integral over lambda equal to 0 up to infinity of lambda to the alpha minus 1 e to the minus lambda summation of x sub I dx. So this is just using the property of the gamma distribution fixing the x's. Now, if we multiply both sides of this expression and by x1 squared and take expectations, we have that the expectation of x1 squared over the sum of x sub I to the alpha is equal to the quantity in the right-hand side. Then we can use Fubini's theorem to take the expectation from the outside to the inside. You see we have x1 squared. So when we take x1, the expectation inside the integral, the x's do not involve lambda, so we can then separate, take the integral. So what we have is the integral from lambda equal to 0 up to infinity of lambda to the alpha minus 1, expected value of x1 squared, e to the lambda summation I going from 1 up to n xi. Now, you see there's a common factor between x1 squared, common random variable between x1 squared and the exponent, and that's x1, the exponent of the sum. So you can rewrite these as, since the variables are independent, we can write this as in the next line as expected value of x1 squared e to the minus lambda x1 times the expected value of e to the minus lambda summation of x sub I going from 2 up to n. The quantity related to x1 appears here. And the sum of the x sub i's from 2 to n are independent of x1 squared e to the minus lambda x1. Now, this quantity, the expectation of e to the minus lambda sum I going from 2 to n xi, the lambda is basically the Laplace transform, the nth minus 1 Laplace transform of the variables, if you think about it. So what we have is the inside the expectation, lambda to the alpha over gamma of alpha, expected of x1 squared e to the minus lambda x1 times the Laplace transform to the n minus 1 d lambda. Now, if you, another step in another trick here is to notice that this expectation, if you take derivatives with respect to lambda, this is nothing but the Laplace transform at lambda, the second derivative of the Laplace transform at lambda. The first derivative involves taking x1 e to the minus lambda x1, and then when you fix x1 and then doing it again, you get x1 squared. So the quantity that we started with is the integral from lambda equal to 0, lambda to the alpha minus 1 over gamma of alpha, phi double prime of lambda times phi lambda to the n minus 1. So this is the exact quantity, the exact expression for the expected value of x1 squared over the sum of x sub I to the alpha. Now I have a question. How much time do I have?
You have still say as long as you want, because there is no other speaker. No, so please continue. Yes, no. After the time you were accorded, you still having 20 minutes.
Okay, thank you. And let's see. 1 second, I have to look at something here. We are letting beta to be the sum I going from 1 up to n xi to the alpha. This is what we use in order to prove the result. Answering the question posed. Okay, so the next thing is, if we are, lemma 2 involves taking care of the expected value of x1, x2 over the sum I going from 1 up to n of xi to the alpha. And the trick is again using the independence of the variables. And in this case, we have that x1, x2 is independent of the sum from 3 to n of xi. So we can rewrite this by Fubini's theorem into the integral of lambda to the alpha minus 1 gamma of alpha, expected value of x1 e to the minus lambda x1 times x2 e to the minus lambda x2 times the expected value of the quantity that is independent of the first two variables, which is e to the minus lambda summation from 3 to n d lambda. Again, using independence, we can show that the expected value of e to the minus lambda summation of x sub I from 3 up to n is just the Laplace transform of at lambda to the n minus 2. And the quantity that I have here, because x1 and x2 are independent, I can use Fubini's theorem, and I have the first derivative of lambda square, because the variables are assumed to be IIT. Any questions? You can use
the chat, yes.
questions, I guess. Okay, so anyways,
Yeah.
it's good to take a little break.
Yes, yes, but
So,
up to now there is no
I am
question.
open to questions. So these are the key steps on the proof. The proof is almost finished. Once we have these two steps, everything else is just accounting. So I'm going to go through that part quickly and then go to the examples. So again, we go to we want to look at the expected value of Sn squared over x bar to the alpha. And there's a trick here, which is to write the sample variance as the sum of xi minus xj squared for I less than j less than or equal than n, xi minus xj squared over 2. And then we can write this expectation in this form, which simplifies to n to the alpha over 2 expected of x1 minus x2 squared over the sum of x2 by to the alpha. Now, by linearity of expectations, so I have x1 minus x2 squared, so I have the quantities of interest are x1 squared to calculate this expectation, and x2 squared and x1, x2. And you see we have divided over 2, so we can therefore, we get this expression equal to n to the alpha expected of x1 squared over the sum of x2 by to the alpha minus expected value of x1, x2 over the sum of x2 by to the alpha. And then, as I showed before, this is n to the alpha over gamma to the alpha, because I calculated these expectations of each one of these. I put them together and we have the final result, which is the answer to the problem, expected Sn squared over x bar to the alpha is equal to n to the alpha over gamma of alpha integral from 0 to infinity lambda to the alpha minus 1 phi of lambda to the n minus 2 phi double prime of lambda times phi of lambda phi prime of lambda squared d lambda. Okay, so now it's time to do an example to show how one can use this. And this is the way in which one does the situation of stable variables by taking the Laplace transform of the variables and integrating. But I'm going to do it for exponential variable. Okay, so we are going to take xi to be IID exponential with mean 1 over beta. Okay, and we look at the expected value of Sn squared over x bar n. And we're going to show that this expectation is equal to 1 over beta times n over n plus 1. Now, remember that beta is the scale parameter, which is the 1 over the expected value of x. So that's the scale parameter. So this expectation this quantity tells me that Taylor's law doesn't hold when you take the power of x bar to the first at the bottom, because the right-hand side is not invariant over beta. It changes as you change the scale parameters. So nonetheless, I'm going to calculate this expectation to show you how to use the theorem. So So we take the Laplace transform of the exponential, which is a special case of the gamma, is equal to beta over lambda plus beta. We take the derivative of that, that's minus beta over lambda plus beta squared. Second derivative is 2 beta over lambda plus beta cubed for all lambda bigger than 0. So by theorem 1, we put everything together and we get this expectation of Sn squared over x bar to the x bar n to be this integral, which is 1 over beta times n over n plus 1. Now, so let's see. So this is the way you calculate things. You can do this for the heavy tail distributions that Joe Cohen described. Now, the next thing is to calculate the coefficient of variation. In this case, we take gamma distributed variable with shape parameter 1 and scale parameter beta, which basically is an exponential with mean nu and variance nu equal to 1 over beta. And in this case, the variance over the mean square is equal to 1. This is important for what follows. So for the exponential variable, the variance over the mean square is equal to 1. So the coefficient of variation, the parametric coefficient of variation is equal to 1. So we can show by using the same arguments as before that the expected value of Sn squared over x bar squared is equal to n over n plus 1, which is independent of the scale parameter beta, and it's approximately a constant. So this means that for the exponential variable, Taylor's law holds for the power of x bar square, the power alpha equal to 2. Now, so you can, as I said, what we have is we can use this result as an inverse problem. We plug in a distribution into the formula and then find the alpha for which the expected value is approximately a constant. So this gives us which alpha is Taylor's law valid. So this could be used in practice to decide which distribution is appropriate for a given Taylor's law and what the power should be. So you give me a distribution and I can tell you what the power should be. Now, going back to the coefficient of variation, we remember that we said that the coefficient of variation for the exponential with parameter beta bigger than 0 is equal to 1. So the bias of the coefficient of variation square is equal to n over n plus 1 minus 1 over n, which is equal to minus 1 over n plus 1, which for small n could be a large value. So this provides a complement to the usual approach to Taylor's law, in the sense that it tells you exactly what the bias is depending on a function of n, and also in terms if you vary the parameter beta and alpha, you can get a sense as to what the coefficient of variation is and how it affects the relationship between the variables for the variable. Okay, so for small n, this quantity is important. If n is equal to 2, this is going to be 1/3. And the coefficient of variations is 1, so the bias is 1/3, minus 1/3. We can also calculate the variance of Sn squared over x bar n squared. So this is something that we haven't found how to do for the logarithm. One can approximate it, but the variance of the logarithm of Sn squared over x bar square n is bigger than the variance of this quantity, which is of order 1 over n minus 24n squared plus O of 1 over n squared. Now, what follows is a formula for a concentration of measure formula for Taylor's law, which, okay. So this formula, I'm not going to go over the details. Basically, you have different samples and you want to find a measure of how far away the sample variance over the sample mean is from its expected value. So we have a concentration of measure. How concentrated is Sn square over x bar n to the alpha to expectation? And by using Markov's inequality, we have that this is less than or equal than 1 over epsilon square m square times the sum of j going from 1 up to m. So we have the different samples of the variance of w and j. And as an example of this, a special case of this gives us a concentration of measure inequality for the exponential. This is the ratio of Sn square over x bar nj square minus its mean over m is less than or equal than 1 over m times 4 over m minus 24 over n squared capital O of 1 over n. Now, this can be used to test hypotheses. And this is a result that one, as I said, can be used to test hypotheses. And it's perhaps the first concentration of measure result for Taylor's law. Okay, so now the next part. So as I said before, if we have exponential variables, a simulation study shows that the variance of the sample variance over the sample mean of j to the variance of the log of the sample variance over the sample mean, the comparison is as follows. If nj is equal to 2, so if the sample size is equal to 2, then we have points, the variance is 0.08, and the variance of the log is 3.9, so it's very different. Again, when nj is equal to 5, the variance is equal to 0.31019 for the original variable, and for the log is 0.9. For nj equal to 10, we have 0.2 over against 0.257. For nj equal to 10, 20 is 0.15 versus 1.449. I think there might be a typo here. So therefore, this allows users of Taylor's law to get a sense as to when Taylor's law with logarithms will apply, as opposed to the Taylor's law that the approach to Taylor's law that we abdicate. Now, finally, I'm going to talk about, this is just one slide, and we joined work with Paul Ducan, the organizer of this conference, who I thank you very much for the collaboration and for the invitation to this conference. So we have extended Taylor's law to the case of weakly dependent processes. So in a forthcoming paper, we show that Taylor's law with exponent 2 calls for a class of weakly dependent variables with an appropriately defined variance. In addition, we introduce a central limit theorem of the self-normalized empirical version of Taylor's power law. Self-normalized because we have the sample variance, which involves a set of variables divided by the sample mean to the alpha, where the sample mean involves the same variable. So we have a self-normalized process. As advertisement, I want to say that I have a book on self-normalization, so which basically extends the T distribution to the case of dependent variables. So anyways, I just wanted to do that. Sorry. So basically our work, our framework is of interest in the context of ergodic Markov chains, infinite moving averages, arch and gauge models, where the family of distribution is a parametric family. These statistics is proved to be consistent. This consistency result is reinforced by a central limit theorem. And both results together provide us with an asymptotic test of goodness of fit to check whether the corresponding dynamical Taylor's law indeed holds. Our work is mainly developed in the context of dynamical Taylor's law with exponent 2, but the power less than 2 are also considered. Now, I want to remark that up to our knowledge, this provides the first central limit theorem for Taylor's law. Typically, people have a different approach to central limit theorems for Taylor's law, but this is the first genuine central limit theorem, you want to say. Now, I also want to remark that Albrecht and Towles obtained some of the results for the coefficient of variation around the same time we did in a paper. And I think Albrecht is in the audience. So that was a useful paper for us. Now, regarding the citations, I want to talk to just as a reference, give you, there's a Kendall 2004, which contains a survey of the state of the art up to that point. And the original paper that started all this is a paper by Taylor, 1961, which is called Aggregation Variance and the Mean. It appears in Nature in 1961. And that is all for now. And I appreciate your patience. And I'm ready for questions.
Thank you, Professor de la Peña, for this very interesting and complete talk. Thank you very much. So again, clap. And so is there any question? Here we have some, may I just Yes. There is several questions. First, Professor Cohen, he says, Victor, please explain what you mean by dynamical Taylor's law compared to ordinary Taylor's law. That's the
Well,
first question.
yes. I want to say that in this case, I would say that there is no real difference except that we are treating the case of dependent variables, and there's a center limit theorem for this. So the dynamic Taylor law is basically what people use. So I just that's my answer. Now, can we have Paul Ducan make a statement?
Yes, Paul Ducan would like to add a short comment. So
okay. Let me finish answering the questions and then we have Paul talk. Okay, so yes, Kendo wrote also a survey and has done a lot of work on Taylor's law. There is he and one of his authors have a center limit theorem, but the center limit theorem is of a different nature. It's not the typical center limit theorem. It involves the study of Tweedy distributions. So there's something known as the Tweedy central limit theorem, which deals basically with the information of the variables involved, like what happens when the parameters go to 0 and go to infinity. The center limit theorem holds. So this is a subject that I'm not prepared to discuss, but there's a book by Jorgensen where all this is described. And I can get the reference and post it in our website. Okay.
Thank you. So perhaps Paul, you want
to... Yes, I
yeah.
just wanted to complete the answer of Victor. In fact, to the question of Joel, in fact, what I was suspecting is that Taylor's law, in fact, are characteristics for a marginal distribution. And my point is that usually I am working with dependence, and so I was a bit puzzled that that there is some alternative to some Taylor's law, which is just depending on the marginal distribution. So what we did with Victor was a blockwise version of his expression. In fact, mimicking a bit also the nice papers by Hans-Georg Albrecher and co-authors, and in this dependent case. And so we obtain, in fact, not only a simple extension to the dependent case, but really some different kind of Taylor's law. That means we had in mind that in some cases, in some papers of Joel Cohen, there was a Taylor's law exponent, which was like, I don't remember, but something like 1.93 or something, very close to 2 exponent. And so, in fact, if you consider this kind of dependent Taylor's law, then variance is replaced, the marginal variance is replaced by the series of covariances, which is in a case when all those terms are non-negative, it means that it's a bit bigger. And so in this case, the 1.93, maybe I am saying some stupid number, but may become more natural, like an exponent equal to 2. That was what I wanted to explain, and also that in fact the Karamata technique, which also Victor explained me, also can extend, but it's not so nice in the dependent case. So the results are a bit less nice in this case. So I want to thank you, Victor, for your nice talk indeed. And,
well, thank you very much, Paul, for clarifying that.
So I thank you.
Yeah, yeah, I was without my microphone. I was just telling that there was another question by Thierry Huillet, but that was answered by Professor Cohen. It was a question of how many L's you put to Kendall, simply. But so there is no other questions about the talk. And I think that Professor Albrecher summarizes the appreciation of all the audience because he's thanking you, Victor, for this nice talk.